So here we go. Graphs of first derivatives. Increasing is where f prime of x is greater than or equal to 0, right? So what I want to be able to do is I want to be able to look at a variety of these graphs and understand the difference between them. So in the first graph, we're going to look at f of x, and the next graph, we're going to look at f prime of x. You want to try to make a connection between these two and their difference, okay? So if this is f of x, am I increasing or decreasing right now? Increasing. So increasing would be from negative infinity to about what? -5. And then union, what? 2 to infinity. Decreasing, -5 to 2. Local max. -5, 4. Local min. To -3. Okay. Concave up or concave down? Concave down. Concave up or concave down? You tell me when it switches. Where? Right about there? So we're going to call that it switches at approximately -2, +1. And we call that the inflection point, is where it changes concavity. So therefore, it's concave down from -infinity to -2, and it's concave up from -2 to infinity. That's not the question that you're going to get on the AP exam, nor is it the question you're going to get on the test. It's easy to look at a graph of f of x and identify those points. The question is, what if you were looking at f prime of x? And there's where we need to follow our definitions. Things are increasing when f prime of x is greater than 0. So we are trying to state things about f of x. Where would f of x be increasing when you're looking at this graph? -8 to -1. Union, 5 to infinity. Where would it be decreasing? -infinity, -8. Union with? -1 to 5. How do I determine when we have a local max or a local min? Where f prime changes. Local max occurs when f prime changes from positive to negative. When does that happen? Positive to negative. X equals -1. Now, here's the deal. When we looked at the actual graph, we were able to produce the y value. We can't produce the y value here. We don't know how high up or down it happens. We just know at x equals -1, that's where it occurs. Local min, x equals -8 and 5. Concavity. This is where things generally start to fall apart for people, okay? Concavity, we're looking for where f double prime is positive. That's where it's concave up, right? So is this the first derivative or the second derivative? First derivative. So I'm going to draw the second derivative by drawing a tangent line. So this represents the second derivative. It's the rate of change of the first derivative. So is this positive or negative? Is the second derivative positive or negative right here? It's positive. Is the second derivative positive or negative here? It's negative. See that? So the second derivative is positive from -infinity to what? -5. Union, where else is the second derivative positive? 2 to infinity. Where is the second derivative negative? -5 to 2. So when does the second derivative change sign? What were the two spots when the second derivative changed sign? -5 and 2. Does that connect for you all right? Okay, take out your worksheet that you got the other day. Okay, here we go. Let's take a look at this. Okay, please look at this example right here. We're going to look at this graph. We're going to see what the graph of f double prime can tell us. Does f double prime tell us about increasing or decreasing? What tells us about increasing or decreasing? Oh, no. F prime, right? If f prime is positive, then we know it's increasing. If f prime is negative, we know it's decreasing. Does this tell us anything about f prime? No. So we can't get any information from that. Right? We don't know. But we can tell about concavity. So as we're looking at f double prime, the question is, where is the graph concave up? Where is f of x concave up? Well, wherever f double prime is positive. Where's f double prime positive? -infinity and -3, union with? It's infinity. And it's going to be concave down when f double prime is negative, which is going to be -3 to 8. The inflection happens where concavity changes, where the f double prime changes sign. Where does f double prime change sign? At -3 and 8. So this type of exercise, along with what we've been doing before, should be able to help us with these type of problems. Look at this one. You have 40 seconds. You can do it with a partner. Try, ready, set, go. Okay. So this would be your e-learning assignment for tomorrow. Got it? Okay. So I want to give you it enough for where you have an e-learning assignment for tomorrow. You learned how to identify limits. We are going to digress from f prime and f double prime for just a second to talk about limits because they're important for our broader scope, which is to talk about the way the graphs look. So for example, we taught you guys the other day how to graph things that look like this, right? You had a question or two on your assignment where you had to sketch a graph. Well, what about graphs that look like, this? How do we handle those type of situations? In order to do that, we need to talk about limits as x goes to infinity. So, for example, here's what you've learned thus far. Suppose you want to identify a limit. Many times you can simply just plug in a into the function, and that tells you a limit, okay? But think about this situation. Suppose you have x to the n power, all right? Suppose you have x to the n power. You could have a cubic. You could have a quartic. As x goes towards positive infinity, okay, how do these polynomials end? What does the output go towards? As x goes this way, what does the y value go towards? You see that? Everybody agreed? So as long as it's positive, it definitely goes towards positive infinity. Look what happens as x goes towards negative infinity. If it's odd, it goes towards negative infinity. If it's even, it goes towards positive infinity. N is even, then we got infinity. If n is odd, we got negative infinity. Suppose that you have x going to infinity, and in this situation, we'll say that n is greater than 1. Okay, so you have an exponent of like 2, 3, or 4, something like that. We would have, and here's kind of how we express this. You can't really plug in infinity. We don't write this as 1 over x to the infinity, because infinity is not a number. And what we do in order to show that we're plugging in something close to infinity is we use a large n. We say you're plugging a really big number. And I know this may make you uncomfortable, but this is the actual way we kind of describe this stuff. So if I plug in a really large number, and I take x to a really large number, what's going to happen to the denominator? It's going to get really, really big. And if the denominator gets really big, then what does this whole thing? It's really small, so it's going towards 0. Does it matter if it's positive or negative? Does it matter if it's 1 over a really big positive number or 1 over a really big negative number? Either way, it's still going towards 0. Sometimes we have other examples that don't work out quite as well. For example, consider sine of x. Do you remember what the graph of sine of x looks like? So as x goes towards infinity, will the graph ever narrow in on just one value? It just continues to oscillate or bounce back and forth, doesn't it? And so we would say that this limit does not exist. Please do not confuse this with other limits we've looked at. Look at this one. This says the limit as x goes towards 0. This one says as x goes towards infinity. Sometimes as soon as you see sine of x, you're like, oh, well, that does not exist. No, because the limit is x goes to 0. This one, do you remember that? It is 1. Very good. And does anybody remember what sine of 1 over x is? It's the barcode function. And do you remember what the limit was for a barcode function? It was to not exist as long as x is going towards 0. But x is not going towards 0. X is going towards. So look at what happens here. You have sine of 1 over a very large number. What is 1 over a very large number going to become? 0. So you get the sine of 0. And what is the sine of 0, all you great trig students? It is 0. Very good. All right. So my point is that you can't just look at a trig function and automatically say what it is. You got to consider the behavior and look at it through. So cosine of 0 is 1. Yep. Okay, I need to show you all that real quick just so we confirm our learning. We have the unit circle. We're looking at 0. What's the coordinate? 1, 0. Is sine the x value or the y value? Sine is the y value. Cosine is the x value. So therefore, the sine of 0 is 0, and the cosine of 0 is 1. That's what happens. Folks, here's the crazy thing. You already know this in so many ways. Watch. Which one's the graph of cosine? The one on the left or the one on the right? Everybody agree that that's cosine? Everybody agree this is sine? So the sine of 0 is 0. The cosine of 0 is 1. Like, we know it so many we know it so many ways, yet when we ask, we don't know it. It's unbelievable. So anyway. You never made that connection before? Oh, goodness. Oh, wow. All right. Okay. So this is a very, very important process. And what we're going to do right now is we are going to use our knowledge of limits to... What? It's okay. Sometimes what people want to say in this situation is that we use this property where we say, well, you know what, we're gonna plug in infinity. We're gonna find the limit as x goes to infinity of 4x minus 1. First of all, do you know what the graph of 4x minus 1 looks like? Yeah, you do. It looks like this, right? So as x goes towards infinity, y goes towards infinity. If we want to show this algebraically, this is the acceptable practice for showing it algebraically. This is what you need to do. We take the limit as x goes to infinity of, and what you do is you factor out the greatest power. So right now we have x to the first power. I will factor out x to the first power. When I factor out x to the first power, what are we left with? 4 minus 1 over x. Agreed? Okay. And now what I will do is I'll plug in a very large number for x. A very large number times 4 minus 1 over a very large number. What is 1 over a very large number? 0. See, that's something we can say with great confidence. Doesn't matter if it's positive or if it's negative. 1 over a very large number will go to 0. And so therefore you will get 4 times a very large number. And now you are convinced that 4 times a very large number will bring you to infinity. Please, please, I understand that I want you guys to be able to think of the graph and know how it behaves. That will not suffice. The algebraic argument is important, okay? So, and we'll try to show you the easiest way. Do you know what that graph looks like? Yeah, so as x goes to infinity, y goes to... Let's confirm that. Limit as x goes to infinity, what do I factor out? X squared. Factor out the largest power. What are you left with? 1 minus 3 over x. So when you plug in a very large positive number, you get a large positive number squared times what? 1 minus 1 over a very large positive number. I'm sorry, 3. What is 3 over a very large positive number? 0. So you end up with a very large positive number squared, which is infinity. What's different about the next example? You're going to negative infinity. So I can factor out the x squared, and I'm left with what? So look at what happens here. I take a very large negative number, a very large negative number, and I square it, times 1 minus 10 over a very large negative number. What happens if you take a very large negative number and square it? It becomes a positive number, so n squared, times what remains here? Just 1, right? Because this becomes 0, so you just get n squared, which is infinity. Seems like there are just always positive or negative infinity, doesn't it? And that's not the case. This is the beauty that you need to watch as it comes to life. Look at this situation. People plug in infinity here, and they're like, oh, well, that's 2 times infinity over infinity minus 1. Well, 2 times infinity is infinity, and infinity minus 1 is infinity, and I get 1. Or infinity. Or 0. Or what the heck do you get? Folks, the word calculus comes from the ability to calculate the infinite and the infinitesimal, the infinitely large and the infinitely small. So I ask you, do you remember when we encountered this? We got 0 over 0, and you said, don't know, right? No, you never said no, soul. I'm pretty sure you said it, and then you laughed. We said 0 over 0. Sometimes it's 1, sometimes it's 5, sometimes it's negative pi. It's all sorts of different things. We're going to show you today how to calculate infinity over infinity. And you're going to have fun. I factor out the large term from the top, which is x, and that I'm left with 2. I factor out the largest degree term in the bottom, which is, and I'm left with what happens to the x's? We will allow them to cancel off. And we'll take the x's that remain and we will plug in n. And we get 2 over 1 minus 1 over n. What happens to 1 over n? Goes to 0. So you're left with 2 over 1, which is, look at that. We took infinity divided by infinity, we got 2. This one, you can plug in negative infinity. Think about this one. You take negative infinity, you take a negative large number to the third power. You're going to get positive or negative. A negative, right? You're going to get negative infinity on top. Look at on bottom. You take a large negative number and square it, and you're going to get positive. We're going to get infinity on the bottom. What's negative infinity divided by infinity? That's a great question right now. We have no idea, do we? We're going to make it super easy, Josie Strong. What do you think I factor on the top? Awesome. Factor out an x to the third. What are you left with? Good. Thank you for your enthusiasm. Now, what do we factor out of the bottom? X squared. What are you left with? Great. Folks, let's save ourselves some time here. What's going to happen with the 1 over x cubed? It's going to go to 0. What's going to happen with the 3 over x squared? What's going to happen with the 2 over x? 0. And what's going to happen with x cubed over x squared? You're going to end up with just x in the numerator, right? So you end up with 4x over 1. Would you agree? What are you going to plug in for x? No. Negative n. So we get 4 times a very large negative number. Negative infinity. In that situation, negative infinity divided by infinity came out to be negative infinity. Folks, there's different levels of infinity. We got to push to the end. We are totally strapped for time in this class, without a doubt. What do you want to factor on the bottom? Good. You get x squared times what's left? Good. So Riker is seeing right now that what happens to these extra terms? Yeah. Sorry. To Riker's point, does it matter? Because it goes to 0, 0. And so you notice you get 6 over x squared. What are we plugging in for x? A negative large number. So you end up with 6 over a very large number squared. 0. Flip it over. You try those three. Go. Folks, I'm going to actually work them through, but I want to show you how you can predict it from the very beginning. Look at this one right here. Now, 1 billion, that's a large number, but is it really that big compared to infinity? Infinity laughs at numbers like 1 billion. Infinity laughs at our national debt. Think about that. Okay? Yeah, it does. So, folks, where is the greater power? In the numerator denominator. So, therefore, it will be 0. Watch, we'll show you how it happens. I factor on x to the 4th, and I'm left with 9 plus 1 billion over x to the 4th. And in the bottom, I factor out what? X to the 5th, and I'm left with 1 minus 1 billion over x to the 5th. Again, 1 billion doesn't compare to infinity. So what do we do with these? We cancel them off. And in the top, you'll be left with 9. In the bottom, you'll be left with x. And so when you plug in that large number, you can see you'll end up with 0. So you still must show the work because it says confirm your answer algebraically. However, you can predict ahead of time. Where's the larger degree? Numerator or denominator? They're the same. So I'm going to make a prediction right away. 4x over negative 6x, that's going to give me negative 2/3. Watch, we'll show how it happens. What do you factor out of the top? And I'm left with 4 minus 1 over x. In the bottom, I factor out x. I'm left with 5 over x minus 6. So I go through and I get rid of the x's, and then 1 over x, 5 over x is gone. I get 4 over negative 6, which is negative 2/3. That's what we predicted. So we will pick up this video. Folks, I just want to warn you, on Monday when we get back, we're going to pick up with the second half of this, but we are also then going to get into our next piece. I'm trying to save us so that we don't, otherwise we're not going to get through the semester. Like, we want to end the semester on a good note. We got stuff to get through, okay?